Alright, so in this video I am going to be reviewing the June 2012 Mechanics, Materials and Waves paper, or Unit 2. So let's start off with some mechanics, just looking at basic scalars and vectors. So it wants us to state two vector quantities. So there are many we could go for, but the classic ones you'd go for are displacement, velocity, acceleration, force, you go for momentum. Those would be your classics that you could go for essentially your vector quantities. Then moving on to scalars, again, loads to choose from here. You have distance, speed, energy, mass, time. All of these things are scalar quantities, so would be appropriate answers to this question. Okay, so we've got a helicopter shown in the diagram. It's moving horizontally through the air, so the resultant force in the vertical direction at least must be 0, and the lift force is labelled A, so we can see that that's at an angle. Name the two forces B and C that also act on the helicopter. So we've got a force acting against the motion, so that's going to be air resistance. And then C, we've got acting downwards, so it's going to be the weight force there. Those are your two forces that are going to be acting on in addition to the force from the rotors. Okay, so let's carry on. Okay, so the force vectors are also shown arranged in a triangle, as in figure 1b. That must be on the previous one. State and explain how figure 1b shows that the helicopter is moving at a constant velocity. Okay, so if you look back on the previous page, you'll see that the vectors form a closed triangle, and if they form a closed triangle, it means the forces are in equilibrium and that the resultant force is 0. So those are the points I would make there. All right, and a little bit I added on the end is actually why that means constant velocity, because according to Newton's first law, if resultant force is 0, the velocity will stay the same. So a lift force A is 9.5 kilonewtons and acts at an angle of 74 degrees to the horizontal. Calculate the weight force of the helicopter, giving your answer an appropriate number of sig figs. So what we've got is the force A, which is up that way, and you've got this angle in here, 74 degrees. The weight force would be acting vertically downwards like this. So what we need is the vertical component of the force A. So that's going to be equal to W if the resultant force is 0. So that is 9.5. You can see the answer at the end is just in newtons, so let's convert the answer into newtons as well. And then we want to multiply by sine of 74 to get the vertical component. And then when we do that, we end up with 9132, but we need to give it to 2SF, so it's going to be 9.1 times 10 to the 3 newtons, or 9.1 kilonewtons. We could have written that there. So that finishes question 1. Okay, so let's flip over. So in the 17th century, when thinking about forces, Galileo imagined a ball moving in the absence of air resistance on a frictionless track, as shown. Galileo thought that under these circumstances, the ball would reach position C if released from rest at position A. Position C is the same height above the ground as A. Using ideas about energy, explain why Galileo was correct. So we know that total energy must be conserved. So it starts with a fixed amount of GPE and then finishes when it reaches the top of it with just GPE. So the first GPE must be equal to the final GPE if there's no resistive forces acting on it. So let's put that into words. Alright, so let's talk through what I've got here. So we're starting with just GP A, because it's stationary. As it rolls down the slope, that's transferred into kinetic energy, and then as it rolls back up the slope, it's converted back into GPE at position C, where it's stationary. There's no work done against resistive forces. Using conservation of energy, initial GPE and final GPE must be the same. But if you remember, Galileo's hypothesis was about height, so let's link that into height. So if M and G stayed constant, that must mean the heights are the same, the GPEs are the same. Okay, so that would be my explanation for that one. Okay, let's flip on. Okay, so Galileo then imagined that the track was changed to this one here, so we've taken away the slope up. Slope B was now, beyond B is now horizontal. On the axis below, sketch a speed time graph of the ball from its release at A until it reaches position X as shown. So if we talk what's going to happen, on this part it's going to accelerate, but its rate of acceleration will decrease. And then here it will be going at constant speed. So let's sketch that. So if we put B on our axis, somewhere like here. So we said it initially accelerates, so that means it would have a positive gradient, but the rate of acceleration is going to decrease, so our gradient's going to decrease. So that's the first section. Let's try again. And then once it reaches B, the weight force is now perpendicular to the motion of the object, so the weight force can't cause it to accelerate anymore, so resultant force is 0 in the horizontal direction, so then speed stays the same at that point. So that's what we get with the graph there. So let's crack on. So Newton later published his 3 laws of motion. Explain how Newton's first law of motion is illustrated by the motion of the ball between B and X. So the first thing I would say is that in the horizontal direction, the resultant force is 0, therefore acceleration is 0, therefore velocity stays the same. Or in terms of looking at the motion from the graph, we know that the ball is travelling in a straight line at constant speed, which means acceleration is 0, which means there's no resultant force. So we can kind of argue it using Newton's second law, which is what I talked about first, but this question wants Newton's first law, so let's talk about that second part. Okay, so, all right, so that's what we've got there. So I picked out specifically what I said to do with Newton's first law, because that's what's relevant. So it's going at constant speed in a straight line, or you can also say at constant velocity. So according to Newton's first law, there is no resultant force acting on it if motion is uniform. And we can see that that matches up. So when it's traveling horizontally, we know the weight force is now perpendicular to its motion, so there's no resultant force in the direction of motion. So that fits with what we're seeing there. All right, so let's move on to question 3. All right, so in this question, we're looking at a sprinter, and they're initially stationary, so they're in equilibrium. We've got several forces acting on it, so at the fingertips and each of the feet. And we've got some values for the force at forward foot and the weight force, but we don't know X and we don't know F at the moment. So calculate the moment of the sprinter's weight about the fingertips. So the weight is a perpendicular distance of 0.26 and the actual weight force itself is 520. All right, so moment is force times perpendicular distance between the line of action of the force and where you're taking moments about. So the force was 520. The perpendicular distance was 0.26. So when we calculate that, we end up with 135.2. So that will be 1.4 times 10 to the 2 Newton meters is the unit of a moment. So then by taking moments about her fingertips, calculate the force on her back foot X. So essentially, because she's stationary, what we can do is we can apply moments in equilibrium. So therefore the moment going clockwise must be equal to the moment going anti-clockwise. So if we look at the diagram, you can see X and Y are acting to rotate anti-clockwise, and W is acting to go the opposite direction. So what we've got is the moment of W on this side is the moment of Y plus the moment of the force at X. So we can say the force at X times by the perpendicular distance for X is going to be the moment at W, which we just calculated, minus the force of Y times the perpendicular distance of Y. So this was 135.2. This one is 180 times by 0.41. And what we can do is then calculate the force at X. So it's our value for this one, which comes out at, let's just calculate that, which is that was 61.4. So that's going to be 61.4 divided by the distance of the force X, which is what do we have here? 0.63. And that's going to be equal to, so we get a value of 97.46, blah, blah, blah. So that's essentially 97 newtons to two significant figures there. Okay, so let's move on to the next part. So now it wants us to calculate the force F. So essentially, the upward forces must equal the downward forces. So essentially, X plus Y plus F, which are all acting upward, must be equal to the weight force. So we've got all of these, so we want to find what F is, so it's going to be the weight force, 520, minus the force at X, sorry, what's it, 180, minus 97 point, blah, blah, blah. And we get 242, so to two sig figs, that's going to be 2.4 times 10 to the 2 newtons. So what we've essentially done there is made the upward force equal to the downward force because it's in equilibrium. Sprinter starts running and reaches horizontal velocity of 9.3 meters per second in a distance of 35. Calculate her average acceleration during that thing. So this looks an awful lot like a Suvat equation. So we've got a displacement of 35. So she's going to be initially stationary. Final velocity is 9.3. Acceleration is what we're trying to find out, and time we don't know. So that's the information we've got to solve this question. So what we want is an equation without t in it. So that leads us using this equation right here. So we can get rid of the u squared because we know it's 0. So acceleration, so average acceleration, or assuming acceleration is constant, is kind of the same thing. So it's going to be v squared over 2s. So that's going to be 9.3 squared for 2 times 35, and if we do that, we end up with 1.2356, so that's going to be 1.2, two significant figures, which would be appropriate here. Calculate the resultant force necessary to produce this acceleration, so we're going to use Newton's second law. So we had her weight force was 520, so we're going to need to divide that by 9.81 to get her mass, times by 1.2356. So when we calculate that, we get a value of 65.49, so essentially 65 newtons to 2 significant figures, and that completes question 3. Okay, so we're looking at a cross-section of an optical fibre, so we're going to do some total internal reflection in this question. We've got an angle of incidence shown up here. We've got another one over by Y. We've got some stuff labelled X and Y. Okay, let's have a look. We've got some refractive indices. So name the part of the fibre labelled X. So that is the cladding, because it's on the outer part of the optical fibre. So that's cladding. And then it wants to calculate the critical angle for the boundary between the core and X. So it's going from the core to X. So your equation for the critical angle is this one right here, because the angle of refraction is 90 degrees. So the critical angle is going to be the inverse sine. So it's going from the inside to the outside. So it's going from Y to X. So it's going to be 1.41. And it's going to be from 1.46. You know it has to be that way round, otherwise you'd be trying to take the inverse sine of a number greater than 1. So that's another way of checking. And then once we do that, we get a value of 74.96. So we can give it to 3 sig figs because these values are 3 significant figures. So we can go that would be 75.0 degrees there as your critical angle. And we can see that we're going to get refraction because the angle of incidence up here is 85 degrees. So that works with what we've got. Okay, so we've got the ray leaves the core at Y. At this point, the fibre has been bent through an angle of 30 degrees as shown. Calculate the value of the angle I. So I'm just going to flip back so I can have a look at what it's talking about. Okay, so what you can see on your diagram is effectively you've got a triangle like this, where this is the angle of reflection, so it's got to be equal to the angle of incidence. This is 30 degrees, we know, and this is I. We know all the angles of a triangle must add up to 180. So if we add 85 and 30, we get 115, which means that I must be equal to 65 degrees there. So don't forget about your triangle laws from maths, you still need those. And it wants us to calculate the angle R. So we've now got the angle of incidence, so we can essentially use Snell's law. And we've got some values to plug in there. So we know N1, we know N2, so if we rearrange, so take the inverse sine, N1 sine theta I all divided by N2, that's going to be sine to the minus 1, we're going to have 1.46 sine 65, that's our angle of incidence, and then on the bottom line we're going to have 1.41, and then that gives us an angle of 69.79, which is 70 degrees to 2 significant figures, because we've used this angle in here 65, so now we can only give an answer to 2 sig figs. All right, let's carry on. The core of another fibre is made with a much smaller diameter as shown, but otherwise everything else is the same. Explain one advantage associated with a smaller diameter core. So the reason you make your core narrower is to prevent multi-path dispersion, the advantage of which is that you don't get pulse broadening occurring on your signal. So what the advantage is no pulse broadening, or another way of phrasing that it would be no multi-path dispersion will occur. It's actually less. Let's not speak in absolute. So less pulse broadening, and less multipath dispersion will occur. So we've stated the advantage. So in terms of explaining it, there's going to be there are the difference in potential distances traveled by the light is smaller. So you should remember here that pulse broadening is caused by the fact light can take different paths and therefore different distances and arrive at different times. But if you make it narrower, the range of possible distances gets smaller, so the pulse broadening effect is reduced. So that's an advantage. You'd go there. The other thing you do is you increase the angle of incidence, so it's less likely to be below the critical angle. That's another advantage you have there, and you're likely to get a faster signal because it's going to take a shorter path to the end. So there's a few things you can write, but that's what I would go with there. Okay, so describe an experiment to accurately determine the spring constant of a spring that is thought to reach its limit of proportionality when the load is about 20 newtons. Include any details of measurements and calculations and describe how you would reduce uncertainty in your measurements. There's a space for a diagram should we want one. So you should hopefully have done this experiment as part of your classwork. It's not the most exciting experiment in the world, but hey ho. So let's put our spring in here. And then what we do is we hang some fixed masses from it, and you'd want to, for safety purposes, clamp your clamp stand to the bench so it can't topple over. So that's your basic setup, and then you'd have so let's label that as it instructs us in the question. So this is your spring, this is your fixed masses, and then what we've got here, you've got your clamp, stand, and then right at the bottom here for safety I would have a G clamp in here as well. Those things just make sure it can't topple over. Okay, so that's your general setup. So what we're going to do is we're going to change the mass we've got hung on it and then measure the extension. To make it as accurate as possible, I'd use a vernier scale to measure the extension. So first of all, we're going to need to work out what range of masses we can use. So the maximum mass is going to be 20 divided by 9.81, which is roughly 2 kilograms. So the maximum mass wants to be under 2 kilograms. I'm going to keep it under 1 kilogram just so we're absolutely safe. So what we're going to do is start off at 100 grams. Why not? Okay, so that's what we're going to start off with. So we're going to work towards a force versus extension graph. So the force applied would be 0.1 G, and the extension we can find using a vernier scale. That would give us an accurate way of determining the extension there. You probably didn't use a vernier scale when you did this in class, you just use a meter ruler, but it did specify we want to reduce uncertainty and make it accurate, so that's why I've picked that. So then what we're going to do is we're going to do this for some other masses. So okay, so then we're going to repeat that process with masses getting bigger, so 200 grams, 300 grams, 400, blah, 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 up to 1 kilogram, so it's nice and safe. And then we're going to do the whole experiment again, so we've got average extensions for each load. Then finally, we're going to get onto the graph. All right, so we can then get our spring constant from our graph. So let's check we've met all the criteria. So I wanted to explain how we do it accurately. We've used a vernier scale, we've taken repeat readings and got an average. Good stuff. We've kept the load below the limit of proportionality. Fine. We've got the measurements we take, the mass and the extension. We've got calculations we've used. Yeah. We've explained how we'd reduce uncertainty with the vernier scale and repeats and average. That's all fine. And we've got a diagram, so that's grand. All right. So continue on. We've got two identical springs, and each of them have a spring constant of 85. And we've got two configurations, series and parallel, but the same load in each case. Calculate the extension for the parallel arrangement. So the extension is going to be the force divided by the spring constant, so 15, and in parallel they add together, so it's 85 plus 85, and that gives us essentially 15 over 170, which is 0.882, so 8.8 times 10 to the minus 2 meters there when they're in parallel. Okay, calculate the extension in series. So first let's find out what the spring constant is. So this is how you add together springs in series. So once you do that, you get a value of K of 42.5. Once we do that calculation, so an extension is force divided by the spring constant, so 15 over 42.5. We do that calculation, comes out as 0.3529, so it would be 0.35 to 2 significant figures there, which would be appropriate. Calculate the energy stored in the parallel arrangement. So the work done to stretch it, and we're going to assume there's no energy loss, so therefore the elastic potential energy is half K extension squared, so it's half times 42.5 times by 0.3529 squared, and that comes out as oh no, I'm being a wally. It says the parallel arrangement, not the series arrangement. So let's get the actual right values. So the spring constant was 170 when we put them both together. And then the extension was 0.0882 squared. And when we do this correctly now, we end up with a value of 0.6615, which is 0.66 to 2 significant figures. Alright, so to finish off question 5, without further calculation, discuss whether the energy stored in the series arrangement is less, greater, or the same as in the parallel arrangement. So I think the equation that will help us here is a slightly different one, that the energy stored is half force times extension, because we're applying the same force in both cases, so we can just compare their extension, so we don't need to do any more calculations. So the series has a larger extension for the same force, so it is going to have the most energy stored. Okay, so let's get that down. Alright, and so that's the explanation. So the force is the same, extension is greater, therefore energy stored is greater, using this equation right here. Okay, so that finishes question 5. A note is played on a violin. It produces what the sound it makes contains lots of fundamentals and a fundamental and some overtones. And we've got the shape of a stationary wing that is one of the overtones. The positions of maximum and zero displacement for one overtone are shown, A and B are fixed, so they're made to be nodes. X, Y, and Z are points on the string. Describe the motion of point X. So X will be vibrating up and down. There'll be no movement left and right, and it will always be moving perpendicular to that equilibrium position we can see. Okay, so let's put that down. That's what we've got there. Whatever you do, do not fall in the trap of saying it's oscillating perpendicular to the direction of wave propagation or energy transfer, because obviously the wave isn't going anywhere because it's stationary, so we have to use the equilibrium line as the reference for a stationary wave. Okay, so state the phase relationship between X and Y, X and Z. So X and Z are both above the equilibrium position, so those are going to be in phase with one another. X and Y are essentially on opposite sides of the equilibrium position, we can see, so they're anti-phase with one another. So let's get that down. So X and Y, I just said, were anti-phase, phase, or 180 degrees out of phase with each other, and then X and Z are both in the same position above the equilibrium line, so they're in phase. In a stationary wave, you are either in phase, anti-phase, those, or you're at a point that's not vibrating at all. Those are your options there. Okay, so the frequency of this overtone is 780 Hertz. Show that the speed of a progressive wave on the string is about 125. So we need the wavelength. So we know two wavelengths is 320 millimeters, so one wavelength is 160. Okay, so speed is frequency times wavelength. So we've got the frequency here, so 780, and the wavelength is 160, but it's in millimeters. So when we calculate that, that comes out as a value of 124.8. So the values we've got here are 3 sig figs and 3 sig figs. So we'd give an answer to 3 sig figs 2. So that's 125 meters per second there. I had a quick look in the mark scheme just now, and for some reason it's saying you must give a 4 sig fig answer. That's absolutely mental and wrong. There's no reason to give a 4 significant figure answer for this. All your data is to 3 sig figs. No idea what that's on about. Please do ignore that. Then it wants us to calculate the time taken for the string at point Z to move from maximum displacement back to 0 displacement. So that would be a quarter of a cycle or a quarter of a time period. So let's first calculate what a time period is, which is 1 over the frequency. That's 1 over 780. We want the quarter of a time period, which is 1 over 4 times 780. And if we calculate that, that comes out as 3.2 times 10 to the minus 4 seconds. You'd expect to be pretty short because we've got 780 of them a second, and that's the value. So the violinist presses the string at C to shorten the part of the string that vibrates. This is like putting your finger on the string on a guitar, like on a fret. State the name given to the point on the wave midway between C and a B. We can see that's a point of maximum displacement, so that is going to be an antinode. Hopefully no surprises there. Maximum displacement point on a stationary wave is called an antinode. Calculate the wavelength of this stationary wave. Okay, so we can see, so we've got some values up here. So the distance between C and B is 240, and we can see we've got half a wavelength. So wavelength is going to be 2 times by 240. What unit does it want it in? It wants it in meters, so times 10 to the minus 3, and that comes out as 0.48 meters, and 2 sig figs would not be appropriate here. 3 would be, because it's 240. Okay, so that's that one right there. Then it wants to calculate the frequency when we've still got the same speed. So frequency is speed divided by wavelength. So 125 divided by 0.480, and that comes out as 260 Hertz. I can leave it without changing it to standard form because 3 sig figs is appropriate for the answer here. Okay, so let's move on to question 7. Okay, so we've got two waves in which a wave can travel on a slinky string. So we've got a transverse wave up here at the top, and we've got compressions and rarefactions. So we've got a longitudinal wave down here. State and explain which wave is longitudinal. We can see the oscillations are parallel to the direction of travel of wave B. That's how we know it's longitudinal. All right, so that's that one. On figure 10, clearly indicate and label a wavelength of B. So it will be the distance between the centers of compression. So there's the center there, the center there. So that would be your wavelength there. That would be a wavelength we could have done from the middle of two rarefactions. That would work too, but I think it's easier to do from the middle of compressions. Use arrows to show the direction in which the points P and Q are about to move as each wave moves to the right. So P, if we look at the direction here, so we can see what's coming next for P is here. So P is going to move upwards. So I guess it wants us to show, let's do it in red. So P is going to move upwards like this. So there's about to be, if we look at it, this part is going to unstretch. This part is going to be compressing on here. So what's going to happen is that Q is going to end up being pulled into the left, because what's going to happen is this part now becomes the region of maximum compression. So you can see Q is going to get pulled into that region. That's how I think about it. Tricky question, that one. Nice. Okay, so electromagnetic waves are similar in nature to wave A, so transverse. Explain why it's important to correctly align the aerial of a TV in order to receive a strongest signal. This will be due to polarization. So transverse waves can be polarized, and they are when they're used for transmission. So you need to make sure the aerial is lined up in the same plane of polarization. All right, so that's what we've got there, and that completes this paper. If you spotted any errors or things that aren't clear, please do comment and let me know so I can clear those up for you. I hope you found this useful, and do check out my playlists on Unit 1, 4 and 5 in addition to the other Unit 2 videos I've got on here for help with those different topics. But thank you very much for taking the time to watch, and I'll hope to see you again.